the launch is like a 12-minute car crash. So Cole, the founder of Orbital, he likes to tell the story that, look, it's like you have a Christmas tree, you've got all these ornaments on it, decorated, and then you want to put it in a 12-minute car crash, and then hope that after the crash, it's all still intact.
Yes.
That's, satellite engineering in a nutshell.
Hi, and welcome to T-Minus Space Daily, joining you from Commercial Space Week. And joining me now is my guest, Amolak. Did I say your name correctly? Amolak, thank you so much for joining me today. Please tell me a bit about yourself, how you started to found your company, all of that, your professional journey.
Thank you. It's great to be here. So my name is Amolak. I'm the co-founder, CEO at Orbital Composites. Full credit to the founder, Cole Nielsen.
Oh, I apologize.
And I always consider myself the co-founder because he's the one who started the journey. And we have a funny story how we met, but maybe that's for another day. But
no, you can't do that.
Let's get into that. So
Yeah.
our kids went to the same school, and I spent 18 years in semiconductors industry. So did all kinds of roles, took new products to market, built new products, and a lot of those products are currently involved in the AI revolution.
Yes.
Fiber optics and advanced ASICs.
Yeah.
So from there, I'd done 18 years of all kinds of exciting things. And I was thinking about doing something new. And right around that time, became an angel investor, joined Sandhill Angels in Silicon Valley. And then I met Cole because our kids went to the same school. And we met at the school picnic.
That is an unusual story. I love this.
And to be honest, most of what he said went over my head the first time. But there's something about him that kept me coming back to him, just to learn, right? And so I spent a bit of time, and I started realizing, I may not understand everything he's talking about, but I believe in him.
Yeah.
Right?
Yeah.
And that's how I joined in. But his story is actually even more remarkable than mine, because, he spent younger part of his years coming through a very difficult time in a childhood, but somehow he found a way to hang out at Stanford around many of the old retired, original Silicon Valley people.
Oh, the legends, yes.
Like Bob Twiggs, who's known as the one of the fathers of CubeSats, right? And many others who invented and built these incredible industries from the early days. So he came up through that. I grew up around a lot of original Hewlett-Packard people.
Oh, yeah.
So we have sort of this, both of us independently got schooled by these, what I call original Silicon Valley hard, deep tech people.
But hardware guys.
Yes.
Yeah.
Yeah, like advanced hardware, like really at the edge kind of problem statements.
Yeah.
So he then went on to, so he was shooting rockets at young age, helping all the Stanford students with their homeworks. But in essence, he was doing a lot more, learning a lot himself. So phenomenal story from there, and then he goes on to Embry-Riddle, right here.
Not bad, right? Not bad.
And gets dual degrees in spacecraft physics and computational math. And then goes back to Silicon Valley, and in his bedroom starts Orbital. So I joined him when he was still in his bedroom/garage.
Yeah.
And just started hanging out with him and started learning. So I'm actually an RF engineer by trade, my original schooling. And he showed me something called a quantum antenna.
So RF as in radio frequency?
Yes.
Okay, just checking. Okay, yep.
And he said, I've got this thing in my garage. It's a 30 gigahertz antenna. I'm like, you gotta be kidding me. How do you make this? He said, oh no, I just printed it. I'm like, what? That's not possible. So that's sort of led my discovery process of like, what is he really up to? and
The mystery deepens.
Yeah, because because what? So I'm a curious person. So I take this so-called printed antenna, and I take it to the best RF people I knew.
Yeah.
And I came from Agilent. They know their RF.
Yes, they do. Yes, indeed, they do. Yep.
Right, which is now Keysight.
Yep.
Those experts told me that, look, you're wasting your time. This thing is not going to work because it does not look like a traditional antenna. But then we got very fortunate. We solicited some support from L'Oreal, Space Systems L'Oreal, and they helped us test the antenna. And then we realized, well, it worked, but it breaks all the rules of traditional RF. So as an RF guy, I'm like, I'm just going to listen to this guy.
Yeah.
So that's how I got hooked into Orbital, and then really started. I'm very operational and customer focused.
Yeah.
And Cole is the visionary, and he can invent and then actually build these products. So we make a very good team, and then step by step we start building our core technologies.
Okay, I'm all in completely. Like you started with a mystery of something and it actually works, but it shouldn't. Okay, super in. So tell me about what you all are building because it is fascinating.
Yeah, so it gets even more crazy because
so here for this.
This is the first talk I was talking about when I met him at a school picnic in a park. He starts telling me the stuff about, we're going to print spaceships in orbit. And we can do everything. We can print the structures, we can print the rocket nozzles, the propulsion things, radiation, whatever. It doesn't matter. We can do it all. We're going to print the interplanetary transport system directly in space because that's the future. And this is about a decade ago. And you can imagine the initial response for most people is like, oh, obviously that's impossible. But, what I did was I just spent some time peeling the layers and really starting to understand what is he talking about.
How would that work? Yeah.
How would that work?
Yeah. So
that's the goal, right?
Yeah.
The goal is to be able to, put people on Mars. To do that, you actually need to build things over there.
Yeah.
And to even get to there's a lot of advantages to build these things directly in space. So in space manufacturing, in our mind, is the next big, hugely disruptive technology after reusable rockets.
Right. Yep.
Because it's a step function change in the cost of building infrastructure off Earth.
Yes.
Whether in space or on another, celestial bodies, right?
Yeah. Yep.
And it's a hard problem. And but that's the goal we set off with.
Yeah.
And then we peel the layers back.
Mm-hmm.
Okay. So if you want to print a spaceship in space,
with what?
What do you need?
Yeah.
What materials are you going to use? What kind of core capabilities? So if you look at that, the most sort of common materials are you need some kind of material that holds things together. You need something that reinforces it, right? And then you have copper wires because there are signals going around everywhere. Those are the three most foundational things. And when you can put them together in creative ways, interesting things could happen. So, for example, now, if you look at 3D printing, so this is, again, back 10 years ago, or he started actually even sooner than that, in the early 2010s kind of time frame.
Okay, yep.
So he, was like, well, 3D printing is like almost there.
Yeah, 10 years ago it wasn't,
almost there in the sense that, you can make all kinds of shapes, but it's not strong enough.
Right.
It needs to get stronger. So what do? Right? we want to make it stronger by reinforcing it with some kind of reinforcement mechanism.
Right.
Most commonly carbon fiber.
Yep.
But it could be any other types of fibers. It turns out that's not really being done at the time. And even still today, it's pretty rare. So that was one thing. Then the other thing is, 3D printers are, first of all, small. They only kind of print in this X, Y, and
That's
sort of
right.
Z direction.
Yeah. Yep.
So we don't want to be constrained. So then the other part of this was, what motion platforms make sense? So we chose to go with robotics, right? A standard industrial 6-axis robot. But don't stop at one. What if we can use many robots together, right?
Okay, a very complex system.
Very complex system, highly autonomous.
Yeah.
And I call it, actually, because I came from the semiconductor world, I call it the GPU of robotics.
Okay.
Meaning parallel processing, parallel printing. How do you go faster?
Yeah.
You can go faster by printing faster, but that comes at a huge sacrifice of print resolution, right? And other problems. So instead, the better way to go is to go parallel.
As opposed to in serial.
In serial,
I remember.
which is a classic CPU versus GPU.
Right, yep.
Right? And then in the early days, people hated GPUs. Like, we have to program it differently. We can't use our x86 programs. So we're building these collections of technologies, right?
Yeah.
There is the materials aspect. There is how do you move those materials around to make more interesting shapes?
Yeah, so in 3D space, right?
In 3D space, not in planar space.
Yep.
And then there's a scalability aspect. Can you only print inside your little box, or can you make things that actually at the right scale?
Right.
Right.
Yeah.
And you kind of need to address all these problems.
Yeah.
Which are relevant on Earth and relevant in space.
Of course. Yeah, and I would imagine with your background in semiconductors, which is so much material science there, I mean, that feels like a very natural fit. I was saying to you before we started, I was like, when you scratch the surface of space, it's material science all the way down, and it's just, it's amazing to me how many times that adage seems to come true. And have you all had to basically come up with new materials?
So we like to say we don't invent chemistry, but we change the physics. And this is a really important point. And the reason for that is that, first of all, there are very large chemistry companies. And so if you invent new chemistry, it takes a long time to incredibly CapEx intensive to scale that up in production. But even more importantly is the qualification timelines are very, very long. And you can't really easily compete with these material companies. So what we found other tricks, right? And oftentimes what happened is, because in composites especially, the manufacturing is constrained by the manufacturing equipment.
Yep.
So as a consequence of that, people stopped tweaking and playing with the physics. And everybody has limited themselves to the chemistry, right? And so we have interesting materials, but it's because we changed the physics, not the chemistry, which means we can use existing materials that are already qualified
in a very different way,
and do that much faster, but still achieve incredible new effects that are not possible with traditional forms of material.
All right, that is a great tee up to the next question of, so what are those new things that you're achieving? So we've talked about ISAM, or rather you have talked about ISAM.
Yep.
And so you mentioned the antenna. I don't want to give it away a little bit. Just tell me a bit about.
So the long-term goal is building what I call gigafactories in space, right? And the goal is to be able to, instead of launching these mega structures, if you look at what it costs to build space stations, it's tens and billions of dollars. If you look at what it cost us to send a telescope up there, these things are incredibly expensive. Why are they expensive? Because they have to you have to test it to death
Yeah.
before launch.
You can't get it wrong, right?
And you can't get it wrong.
Yeah.
And the launch is like a 12-minute car crash. So Cole, the founder of Orbital, he likes to tell the story that, look, it's like you have a Christmas tree, you've got all these ornaments on it, decorated, and then you want to put it in a 12-minute car crash, and then hope that after the crash,
It's all still there.
intact.
Yes.
That's, satellite engineering in a nutshell. And what
That's a great way of thinking.
ISAM does is it changes that paradigm.
Yeah, it
right?
does.
We initially, ship materials up and just start making things over there.
Yeah.
And start assembling them. And you can start building much larger structures than what's possible and get around your tyranny of launch fairing, right? Even Starship, the launch fairing is still only 8 meters. That's not huge.
Yeah.
We want to build, 100-meter antennas, 1 kilometer scale antennas. You might ask why.
Yeah, for what end? Yeah.
Two of the biggest markets on Earth are energy and communications. Now imagine you want global scale energy, global scale communications. The common denominator between those two things is giant antennas.
Yep. Which
So-
sometimes when we try to send them up, they fail.
They don't
Yeah,
work.
yeah.
Because the biggest antennas we send up are what's called unfurlable antennas.
Yeah.
Basically like your umbrellas. And it turns out those hinges are quite problematic.
Yeah.
And they always get stuck.
Yep.
So there are very large number of commercial and defense satellites up there which never unfurled properly, and they're just sitting there dead.
Yep.
Billions and billions of dollars spent on this. Just most recently, Viasat had this problem.
I was just thinking about them specifically.
Right, that
Yep.
they had this 22-meter antenna.
Yeah, I was very excited about it.
And
then
it just refused to open.
Yep. I remember that story. It was
So that's precisely the problem.
Yeah.
Why deal with that problem? If you start manufacturing and assembling these things in space, you can bypass that problem.
Yep.
But they also have a limit. You can only make umbrellas so large until it becomes problematic. So you'll have a hard limit on how big these can get. We're going to shatter those limits with in-space servicing, assembly, and manufacturing. So the largest markets, global scale communication, direct to cell.
Yep.
Right? There's billions of cell phones.
We're all moving towards it right now.
If your satellites could talk to it, that's a huge market. And then obviously with space-based solar, you can build global scale technology for energy. Common denominator antenna. Now, you need giant antennas, and the only way to really make them at that scale is to make them over there.
Makes sense. Yep.
So we have a great partnership on space-based solar with Vertisolis, which is a startup leading the charge there. And then we're working with the Space Force on the building antennas for other use cases. You need big antennas. If you want to look finer on the ground, big antennas.
Yep.
If you want to look deeper into space, bigger antennas help. So space domain awareness, you need bigger antennas. If you want to go further into space, you want to build a new high bandwidth deep space network, you need big antennas. Big antennas is answer to all your problems in life. So that's how I look at it.
Yeah.
So we want to be the company that figures out how to build giant antennas in space. So now the issue is, ISAM is a complex topic. It's a word that's thrown around a lot.
It's still very also new. It's not new as a concept, but it's still like it's version. It's
people are still trying to figure out what it is.
Yeah, exactly.
So a couple of years ago, we participated in Catalyst Accelerator, which is a Space Force funded accelerator, specifically focusing on ISAM. And and we spoke to hundreds of people at NASA, in DoD, other companies, really a broad swath of people. And we realized that everybody wants it, nobody wants to pay for it.
Yeah.
Because you need a killer application.
Yeah.
And the antenna is the killer application.
Makes sense.
So then we start working backwards. Okay, if that's the end state, what do we need to do? What are the core technologies?
Yeah. Where are you on that timeline too? Like where are you at?
So we have a number of programs right now.
Yeah.
Developing different pieces of the technology. So you need traditional, composite structures. That's one area, and we're advancing that technology by focusing on terrestrial applications. So we have a TAC-5 program with the Air Force, basically on drone production.
Cool.
And we're building that out, and that's accelerating very quickly. And then we get into the second class of composites, which are called either carbon or ceramic matrix composites. So these are really your hot structures, things where you need the temperatures become extreme, like your rocket nozzle or your heat shield,
Yeah, heat
or
shields.
your
Yes. Yep.
hypersonics.
Yep. Heat shields have been very, sorry for the cliche, very hot because I've had a lot of conversations with companies where they're just sourcing good heat shields. It's been a problem.
Thank you for bringing that up. So it's a problem.
Yeah.
I'll tell you why. The problem is the technology has not evolved in decades.
That's exactly it. Yep.
So I hate to say this.
Oh my God, the light goes. Sounds like they're kicking us out.
Yep. With heat shields, the problem is the process is old. And I hate to say this, but we're trying to use basically Apollo era technology for Artemis.
Yeah.
And to me, that's a problem because we have not really fundamentally evolved the technology. And what we're working on is, our goal is to build reusable heat shields. Ablatives are useful, but the big breakthrough in the space industry, just like with reusable launch, we have to solve the reusable heat shield problem. And the answer lies in fiber printing, right? This is because we're opening new design optimization paths that have not existed before because you were limited by the manufacturing process, not necessarily the materials. Materials have always been there, they're still there, but you have to go beyond the materials. We need to start paying attention to the physics. Yeah.
I appreciate you saying that and that correction because that is a key thing that I'm learning from you today. Yeah. That I definitely, you busted a myth in my mind that I had. So I appreciate that. Yeah.
So in a nutshell, we're building all the core technologies for ISAM, whether it comes to advanced materials, manufacturing processes, robotics that work in space, radiation shielding, and the ability to software that manages all that complexity, and then the end application, which is antennas as a starting point, but many other things over time.
It's an exciting place to be. It's fascinating to hear what you all are working on, what you're building. So thank you for sharing a bit about it with me today. I really appreciate it.
Thank you.
Thank you for your time.
Yeah, thanks.
Thank you. This has been fun.